the desalination of brackish water. Okay, uh, Jin Hong, the time is yours.
Thank you, sir. So, hello everyone. As kindly introduced by Professor Liang, the presentation I'll be giving today is on the hybrid PEC and FCDI process. Now, I'll briefly start with the introductions of my research. All right. So, as we all know, with the increasing population, the demand for seawater or fresh water has been continuously rising as always. Now, of the multiple water bodies on Earth, only 5 to 6% are directly usable freshwater, with the rest being mostly seawater. Now, so as we are all aware, the market for seawater desalination has been escalating worldwide. However, the problem with seawater desalination is that it's quite energy intensive. And also, regions with no access to the sea require alternate sources of water supply, so brackish water has been rising as one such source. Now, conventionally, the NF process or the nanofiltration process was widely introduced in regions relying on brackish water to supplement its freshwater supply. Now, however, the NF is also known for its inadequate rejection of monovalent ions. Also, recent studies have revealed that the process shows extremely low rejection for an extensive number of organic contaminants, for example, phenol or nitrobenzene that's commonly found in brackish water. Now, also, the NF is a pressure-driven process, so the NF also consumes high amounts of energy depending on the concentration of the feed water, and is also prone to membrane fouling or the scaling phenomena. Now, meanwhile, with the worldwide movement for a carbon-neutral society, a paradigm shift in the field of water treatment is also occurring, with electrical chemical-based water treatment systems receiving increasing attention. Now, of one such process is the capacitive deionization, and its hybrid form of low electrode capacitive deionization, which I'll be presenting on today, with advantages that can compete against conventional systems. Now, this system is low energy, it's also low carbon or carbon neutral. It has a very high recovery. Now, and also a study in 2013 revealed that the FCDI system or the MCDI system has lower energy consumption compared to the RO, and also it has a very high sustainable operation. Now, however, as implied by the name of the process, capacitive deionization is a process that targets ionic species, and we cannot use this process to remove organics. So thus, an additional unit is required to remove the organic content of the target water. Now, especially brackish water is known to contain a broad range of organic pollutants originating from waste sources such as industrial, medical, and aquaculture farms. Now, so in our study, we have introduced the photoelectrical catalysis, to be called PEC from now, with novel fabricated electrodes for such application. Now, ultimately, the purpose of the work was to investigate the feasibility of the hybrid PEC FCDI system. I'll briefly explain on the configuration of the PEC and the FCDI systems. Now, for the PEC, the anode we used was a TI mesh and a TI plate, and for the cathode was a PT foil. The surface area of the electrodes were 9.5 centimeters squared, and for the light sources, we used 3 different types. It's a 4-watt UVA, UVB, and a UVC. Now, for the electrodes used in the PEC system, they were fabricated on the PI mesh and TI plate under 600 degrees Celsius under cathodic polarization. Now, on the FCDI side, as you can see, the ion exchange membranes that were used were 43 centimeters squared, and the applied voltage was between 0.5 to 1.5 volts. Now, for the flow electrode, we used the activated carbon with a BET of 2000 approximately, and the mass loading of the activated carbon was between 5 to 15 weight%. Now, if we increase the mass loading of the activated carbon within the FCDI system, the overall performance of the process would obviously increase. However, studies in the past have shown that if we increase the mass loading above 20%, the solution leads to clogging of the system because the viscosity becomes much too high. So in our work, we limited the mass loading to 15%. Now, I'll briefly go over the results and discussion part of our research. Now, after the fabrication of our novel BM and BPTNA electrodes, we analyzed the electrodes through SEM, XPS, and XRD analysis. Now, the SEM imagery shown on the left side shows that the successful fabrication of the nanotube arrays was fabricated on the Ti mesh and Ti plate electrodes. Through the XPS analysis, we identified the TiO2P and O1S peaks with high binding energy from the annealing. Also, the XRT intensities also show that anatase and rutile crystalline structure was confirmed on the TNA electrodes. Now, to confirm the electrochemical properties of the two BP and BM TNA electrodes, we conducted the analysis through EIS analysis. Now, the analysis confirmed reduction in the charge transfer distance for the BM TNA electrode, which naturally led to improved charge efficiency. Now, subsequently, organic degradation potential of the two electrodes were evaluated using benzoic acid as a model substrate under 3 different light sources as previously introduced. As you can see from the results, the operation of the PEC system showed a far superior performance for the BMTNA electrode under all light sources. So taking a look at the figure on the left, we can see that using the BMTNA electrode, benzoic acid was nearly completely decomposed, with even the minimum rejection or decompose rate being 80%. But on the right side, we can see that using the BPTNA electrode, the degradation performance was quite low, and even the highest was only up to 80%, with the lowest being around 40%. So we confirmed that the BMTNA electrode showed a much higher photoelectrode degradation performance compared to the BPTNA electrode. Now, to further confirm the feasibility and the performance of the novel fabricated BMTNA electrode, we applied the system using 8 different organic pollutants commonly found in brackish water sources. Many of them include 4CP, BPA, phenol, or the common chemicals that are commonly found in the brackish water. Now, through the analysis, we found that different substrate species, for example, the electron donating group or the electron withdrawing group, exhibited varying reaction rates. The phenolic compounds of the electron donating group more easily release protons into the solution under OH radical-induced oxidation, and were thus more susceptible to the photoelectrochemical analyzation. Now, in contrast, the benzene ring substitution of the electron withdrawing group hinders substrate degradation. However, a long-term operation of the PEC system confirmed that all 8 organic pollutants were successfully degraded using the system. Now, moving on, we evaluated the long-term durability of the electrodes through a long-term operation. Now, the evaluation was conducted for approximately 20 hours, and as you can see from the figure presented on the right, stable performance was confirmed all throughout the 20-hour performance analysis. Now, moving on to the subsequent FCDI part. Subsequently, the FCDI process was initially investigated for the optimal operational conditions. Now, the operation optimization was based on applied voltage and electrode mass loading, and evaluation of the optimization parameters was on ion removal efficiency and specific energy consumption. Now, as we all know, higher applied voltage allows stronger attraction of the target ions, leading to increased removal. Also, higher mass loading also leads to increased removal in that the electrode particles act as a bridge for charge transportation. Now, thus, higher electrode mass loading also allows the formation of strongly defined charge percolation pathways, thereby improving the overall charge efficiency of the system. So as we can see from the figure on the left that shows the ion removal efficiency rate according to applied voltage and electrode mass loading, we can see that the removal rate continuously increases with increased applied voltage and electrode mass loading. However, as I previously explained, having a higher electrode mass loading also increased the electrical current of the system, which also leads to the increase in the specific energy. So that's why taking a look on the right figure that shows the specific energy consumption, we can see that increasing the mass loading and also increasing the applied voltage increase the energy. So comparing these two values, we found that the optimal condition was an applied voltage of 0.8 volts and a mass loading of 10 weight percentage. Now, applying the optimal condition previously found, we ran the operation of the FCDI again through a feed concentration of around 5,000 brackish water concentration. As predicted, increase in the applied voltage and mass loading led to the continuous reduction in permeate conductivity, as can be seen. However, with nominal changes between the 10 and 15%, the optimal condition was confirmed. As you can see from the left-hand figure, that is the increase in the voltage under a 5 weight percentage condition. And the middle figure is the increase in the voltage under 10 weight percentage figure. Now, the increase in the conductivity performance sharply increased from 5 weight percentage to 10 weight percentage. However, increasing the mass loading from 10 weight percentage to the 15 weight percentage showed a nominal change. And since a 15 weight percentage would only lead to the increase in the energy consumption of the system, we thereby confirm that the 10 weight percentage is the optimal concentration for the flow electrode parameter. Now, lastly, we operated the PEC FCDI hybrid process by treating a real brackish water solution to produce organic free permeate that satisfies the freshwater TDS standards. Now, the solution was prepared as a complex solution to more accurately reflect the composition of brackish water. As you can see, organic mineralization by the generation of reactive oxygen species within the PEC stage was observed. As you can see from the figure on the middle, the PEC system shows the complete mineralization of organic pollutant measured through a TiO2 level concentration. And TiO2 levels reached near zero after 40 minutes of operation. Also, no further oxidation byproducts was detected afterwards. Now, subsequently, the permeate of the PEC system was applied as the feed water for the FCDI system. Now, the subsequent FCDI process led to the rapid decrease in the target ionic concentration, with removal efficiency reaching averaging of 80% in the first absorption process. Now, after a desorption process to regenerate saturated active carbon electrodes, operation of the second pass FCDI system obtained complete deionization of the permeate stream. And through this analysis, we confirmed the feasibility of the CFCDI hybrid process for producing an organic-free permeate that satisfies freshwater TDS concentration. Also, the operation was also conducted in long term, and we found that the stability of both the PEC system and the FCDI system was maintained almost even throughout a 24-hour period. Now, conclusively, in this study, evaluation of the PEC FCDI hybrid process was conducted, and a stable fabrication of the superior BMTNA electrode was confirmed. And also, during the PEC system, generation of reactive oxygen species was confirmed, which led to the organic degradation of the model organic pollutants. Also, in the FCDI system, low energy, high performance operation was analyzed via the optimization of the two key operational parameters. And through using this hybrid process, we generated the organic free freshwater that met these freshwater TDS standards, and we confirmed the feasibility of this PEC FCDI hybrid process. Thank you for listening to my presentation, and I would like to thank the National Research Foundation of Korea for granting the funds required for this research. Thank you, sir.
Okay, thank you, Ji-hong. On to question.
So yeah, I have one question, Ji-hong.
Yes, sir.
That's a very interesting hybrid system, PEC and followed by FCDI. So just wondering, it looks like a very challenging process compared to you have ozonation or AOP, just chemical process. Now you want to use PEC followed by FCDI. So what's the cost benefit of this technology? And then, looks like you are saying that brackish water is wastewater use. You try to remove a lot of micropollutants, right? So,
Yes, sir. That's right.
have you ever considered like cost impact compared to AOP chemical oxidation process? What's the benefit of this PC followed by FCDI?
Yes, sir. As you can see, the aim of our research was to remove both the organic and the ions
Yeah.
to uh, basically generate a permeable freshwater standard solution. So that's why using just a oxidation process, we would be able to remove the organics, but then we would need a subsequent process to remove the ions. So that's why in the beginning of my introduction, beginning of the presentation, I said that this hybrid process was compared to nanofiltration. Now, I don't have the exact values prepared today, but for the PC system, we found that the energy consumption was very low. It was around 0.02 kilowatt hour, so it was very low compared to the conventional membrane systems. Also, for the FCDI system, it was also very low. As I said in the beginning, under a 4,000 ppm freshwater concentration standards, the FCDI shows even lower energy consumption compared to RO. So if we compare it to that NF system, it will also be very low. So that's why in terms of the energy consumption, we also found that this hybrid process has its strength and it's feasible for operation.
All right, thank you.
Okay, next question is from here.
Yes, sir. So the question
Yeah.
was,
The light source PPA, light source of PC can be developed for solar energy. If that means the energy input is unstable and quality, and not use the UV light.
mm,
And could you please introduce the quality of the output product? I
okay,
think that means if to change the UV into solar sunlight,
yes, sir.
well, it'd be perfect for the BPA removal.
Uh, well, for the solar energy, actually, this is our future research that we're trying to do. But so if we look at the slides that I'm showing right now, just
Yep.
using the UVA, UVB, and UVC systems, as you can see, if you use a UVC system, the degradation rate reaches almost 40%. So just having the light source is very,
ABC.
excuse me, sir?
What does it mean? ABC.
Oh, UVA, UVB, and UVC sources. So those are the three light sources that I used in this research. Now, just having the light sources only shows a very low rejection or the degradation of organics. So I think for the solar energy too, especially because it's very unstable and it's periodic, so I think it'll show even lower degradation rates. So I'm not quite sure if solar energy will be quite as feasible. And also for the quality of the output water products, from the final presentation slide, as you can see, the organic is completely zero, and that's TOC standards, not the exact concentration of the material itself. And on the ionic part, we can see just running the first pass of the FCDX system removed almost 80% of the entire ion, and having the second pass removed 100%. So if we operate the second absorption phase, actually the concentration of the ion is zero.
Well, one more question.
Yes, sir.
Is the BPA fully degraded or just uh, the trans some of the byproduct intermediate? What about TOC removal?
Sorry, sir, you were breaking in your question.
Yeah, I mean, the BPA is fully degraded.
Yes, sir.
But what about the TOC? This is fully mineralized.
Oh, yes, sir. On the figure I wrote BPA concentration, but it was actually measured through TOC levels.
Oh, okay.
Yes, so TOC was completely removed.
All right. More. Okay. More questions? Let's move to.
Thank you, sir.
I'll give the chair to That's the Hongqiong.